Alright guys, we're going to do a few more examples of limits today, and I want to point out a couple of things that people struggled with, and definitely was a piecewise function and also a compound fraction. So I want to do a couple more examples of those before I do the other things I want to do with you. Here's an example of a piecewise function, and we've got two different equations. We've got this polynomial, this rational equation, if x does not equal 2. This means everywhere else except for 2, we're going to be looking at this graph. And then we've got this single point. When x is 2, y is 6. Now let's go take a look at this picture. What does this look like? We've got this graph here, and we can see this is a piecewise function, and everywhere else we've got that rational function, but at the specific point 2, we're up here at 6. And we're interested in what is the limit as x approaches 2 of this graph. Well, looking at a piecewise function, you need to make sure, all you have to make sure for a limit is make sure that from the right and from the left we're approaching the same value. So we're looking at x is approaching 2. This is where we need to focus in our eyes. So from the right is this black arrow I have here. That means, from the right, where are we heading? And we're heading towards that y value of 4. And from the left is this other arrow. Where are we heading? We're also heading towards this y value of 4. We don't really care what happens exactly at 2. We just want to look around 2, close to 2, in that neighborhood. Do we have a graph that's matching up and heading towards the same y value? That's the intended height of the graph. That's where it's trying to get to. Even though at that point it jumped way up here, this answer is 4. Because that is the y value we're heading for. Even though that y value up there is 6, so we got to get that down. So when you have a piecewise function, you're going to need to graph it and take a look at it. Now, some piecewise functions, though, as we saw from last night's video, don't match up. They don't line up. We looked at the piecewise function last night, and it didn't line up. It had from the left it was -1, and from the right it was 1. Okay, so let's go on and see if we can't do another example here. Alright, I've got a piecewise function, y squared plus 5, if y is less than -2, and 1 minus 3y if y is greater than or equal to -2. And let's take a look at the limit as y approaches, say, 6. Now, if y is approaching 6, we are going to be looking at this bottom function because that's what we use for all y values that are bigger than or equal to -2. So we would just be looking at that one right there. And you can just plug in 6 for y and you're going to get 1 minus 18, which is -17. And that's no problem at all. But where this can get tricky is if I ask you the limit at at y approaches -2. And -2 is where these two graphs meet. And so we would need to know, whether or not these two graphs are trying to meet. Are they trying to head towards the same value? And an easy way to do that is find out the limit as y approaches -2 of both of them. Plug in -2 to both of these functions. So if we plug in -2 for y into the top one, we get -2 squared plus 5, which is 4 plus 5, which is 9. And if I plug in -2 into the bottom function, I get 1 plus 6, and I get 7. And you can see that these are not the same value. So as y approaches -2, the limit does not exist because we were not heading towards the same y value. Alright, this one people really struggled with today, so I want to give an example of this. This is a complex fraction, and these can be fixed or made to look better if you separate it out. And this is what I mean. Instead of doing divided by x, I'm going to do multiplied times the reciprocal. You know that thing we learned in 7th grade? Thank you, Kimmy. That thing we learned in 7th grade to multiply by the reciprocal? And then here, we're going to bring these two fractions together. And I've showed you guys this little shortcut. You can do 5 times 1 is 5. 5 plus x times 1 is 5 plus x. And we're subtracting those. And then you multiply the denominators together. That is a shortcut for bringing those two fractions together. Let's see that again. 5 times 1 is 5. 5 plus x times 1 is 5 plus x, and we're subtracting, so that goes right there. And then you multiply the denominators. And we're still multiplying this times 1 over x. So if we clean up the top, I get negative x over 5 times 5 plus x, and I'm multiplying this times 1 over x. And I cancel these x's, and I get negative 1 over 5 times 5 plus x. And we plug in 0 for x, and we get negative 1 over 25. So let's take a look at one that has a little bit more of an advanced algebra approach, and that's where we have to do a difference of cubes formula. And I'm sure we all remember that, but if you don't, the difference of cube is a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. So for this example, if you plug in 1/2 and you're doing your plug and chug, you're going to end up with 0 over 0. So this is indeterminate. So we're going to factor the top and factor the bottom. So the top factors into 2x minus 1 times 4x squared plus 2x plus 1. And the bottom factors into 2x minus 1 times 5x minus 1. Let me make sure I did that right. 10x squared minus 2x minus 5x. Oh, we're happy. Okay, so we're going to factor something out of the top and bottom, and now we're going to try our limit again. So we're going to plug in our 1/2 for x. So we want 4 times 1/2 squared plus 2 times 1/2 plus 1, and we're going to divide this all by 5 times 1/2 minus 1. So 1/2 squared is 1/4 times 4 is 1. 2 times 1/2 is 1 plus 1. And then on the bottom we have 5/2 minus 1, which is 3 divided by, if I make this one, think about that as 2/2, I'll get 3/2. And we flip it over and multiply, we get 3 times 2/3, and it works out to be 2, and it's C, and we're happy. Last example is finding a value inside the fraction that will make the limit exist. Now for this limit to exist, I need to have a common factor in the top and bottom. Now right now, when we plug in 2 for the denominator, we get 0 in the bottom. For the limit to exist, I also need to get 0 in the top. So I have to figure out what will make the top have a factor of x minus 2. So x minus 2 times something has to work out to be x squared plus ax minus 10. Well, the only other thing we can put in here is x plus something, and what times negative 2 gives you negative 10 would be plus 5. If I have this, I've got x minus 2 times x plus 5 over x minus 2. That would allow me to have what's called a removable discontinuity. You haven't heard that word yet, but we're actually taking out the whole of the graph so that the limit exists. So I had to divide x minus 2 into this quadratic, and that left me with x plus 5. 5 is the only thing I can put in this other factor. So let's figure out what this value of a is. If the other factor was x minus 5, then this will FOIL out or multiply out to be x squared plus 5x minus 2x minus 10, which would be x squared plus 3x minus 10. And so here, a has to be 3. So that is the answer to that. So I will see you guys tomorrow.